on both locations. Was installed on both locations, as you could see on the two bathymetry contour graphs. The blue triangle shows the deployment of the wirewall in Dawlish, and the bottom contour graph shows the deployment of the wirewall in Penzance. In the meantime, several studies have investigated to use training models for weight overtopping prediction. Right. However, they use data sets from Eurotop, so that means these models inherit the shortcomings of Eurotop, since they do not account important variables like wind speed and direction. Well, this is our approach. For starters, we got our data, which is the wave overtopping events for the wirewall system. Then we have our wave buoy data, which are the significant wave height, mean period, peak periods, and mean with wave period data. And also we have our meteorological data, which is the wind speed and direction. And furthermore, we have our water level data. Our second step was to train, test, and validate machine learning models like SGBoost, SVN, random forest, even a multi-layer deep learning perceptron neural network. Also, our wave, wind, and water level data was split in training, testing, and validation data sets. And since we have like imbalanced data sets, because our overtopping events represents the 6% of our total data, and while the remaining 94% represents the non-overtopping events class. SMOD was used to balance our data. Well, the SMOD means like a synthetic minority oversampling technique, right? Also, since our model, since the model presented like overfitting, L1 regularization was used, and also the threshold was adjusted. For the step 3, we have our predictions, right? The overtopping, if there is overtopping occurrence, that means if there is overtopping or not. And also, we got our overtopping frequency. At the end, we have like our splash dashboard, which visualizes our predictions. Well, in this part, you could see the BIM was used to determine to define any relevant feature variable to predict wave overtopping. So that means any relevant feature trained within the machine learning models that reduces the gene impurity was assigned a high importance. So as you could see on the bar graph on the left-hand side, you could see the relevant, important features for wave overtopping prediction on the 2 rigs in Dawlish, right? In the same way, you could see our relevant variables for overtopping prediction for the 2 rigs in Penzance, right? And also you could see on the right-hand side of the slide, you could see the list of all of our relevant variables that were used for our machine learning models. Here, we have our metrics for estimating overtopping occurrence in Dawlish. As you could see, random forest outperformed the SGBoost and neural network because it has like an F1 metric value close to 1, which means it was good at the prediction. And also, as you could see, the recall metric, we could see that random forest, it was able to predict weight overtopping. It was able to predict overtopping events with with good accuracy. Also, we have the accuracy of 96% for random forest at the rig 1. We have a similar scenario for the rig 2 in Dolish, right? It has a good accuracy for detecting overtopping and non-overtopping events. And also a similar scenario we have in Penzance. For the next one. Also, as you could see, these are the results for the regression models to estimate weight overtopping frequency in Dolish and Penzance too. As you could see, random forests also have like a good square metric, which is close to 1, right? Did measures the how good is our model in predicting this overtopping frequency. Since this is the value that is close to 1, this is random forest is still our best models to predict weight overtopping frequency. We have a similar scenario for the second rig at Dolish. So these are our results for weight overtopping predictions. As you could see, we have our 2 rigs per location, and in the x-axis we have hourly predictions, and the blue circles represents the overtopping event that were predicted for the random forest models. On the left-hand side, we could see like some slides that the user could play with in order to generate different scenarios for overtopping prediction. So in this slide, I would like to make a quick comparison between the results in the Jupyter notebook, which shows our predictions, but as you can see, it's not user-friendly, since we could barely see like the time of our overtopping events and non-overtopping events. So here, I will like this.
The scientists applied to the student notebook. So what you see on the left is what the scientists gave us, and what you see on the right is what the RSCT turned it into.
Yes, basically, we built the splash dashboard to visualize in a user-friendly way our overtopping predictions. As you could see, well, it's still sharing. We uploaded interesting data set that has the overtopping events from storm bear, right? And also on in these graphs, well, it's taking some time. Well, as you could see, the blue squares and the blue circles shows the overtopping events, the time, the date, and this dashboard predicts overtopping events from today up to 5 days ahead. Also, the user is able to play with our wave variables, atmospheric variables, to compare different scenarios, right? Also, we have like a legend. We could see different overtopping events at different levels of confidence. We built this splash dashboard in collaboration with the University of Plymouth. And also this project was found by NARC. And also Met Office provides us the meteorological data, the wind speed and direction data sets. So, well, I will pass over.
I can go back to the slides, please. So we've seen that we've now built this dashboard, and the user can select what location they're working on. They can see the current forecast, or if they want to test out sort of future scenarios, they can move the sliders around and then see what the effect of those things happening would be. So the user can play with the water level, the wave heights, the atmospheric variables, and predict new overtopping scenarios. So we built this dashboard, and once the user submitted any variables, it will rerun the random forest model and recompute the output and show it back live on the screen, along with also the sort of the baseline data that they had as well. So the reason it is taking a few seconds to give the response is because it's actually running the model live, whatever those changes are put in. So we also have some sort of longer-term trend graphs that will show the significant wave height and the tide level over time, all again done in the Plotly dashboard. We also employ not just RSCs on this project, we actually have a designer working for us as well, and she did a very good job of making sure that not only had we built something that functioned, but we built something that was accessible. And so we followed some user design best practices to ensure that we had good color contrast, and that we followed the AA standard of the Web Accessibility Guidelines. And we had several iterative meetings with the stakeholders involved to design this user interface. And what we started off with was a user interface which she had designed in Figma, and then the RSC team's job was to then translate that Figma design into a working web application. And I was actually quite impressed with how well the final result looked like the mock-ups that we did in Figma. I think there were a couple of graphs we never implemented, but apart from that, I think it all pretty much looked the same. So just a bit about the architecture of the whole system as well. So we actually have this deployed across 3 Docker containers. So one actually runs the cron job that downloads the data from the Met Office. The Met Office supplies both wind forecast and wave forecast data, which come through 2 totally different means. So the wave data is actually off an FTP site, and the wind data comes from our web API. So we have a Python script that pulls pulls both with 2 separate Python scripts run on the cron, entirely contained within their own Docker container. So once you launch that container, it just stays running and downloads the forecast I think it's every day or twice every day, and saves that to a Docker volume. We then have the back end, which is where the models are run, and that is its own container. And then there's the front end running the Plotly dashboard. So when a user moves one of the sliders or presses one of the buttons, that triggers a web request to the back end, does the updated calculations using that latest data that's available on the volume. And then obviously that will get presented to the user over the internet. So as I said, Splash is using random forest models trained on this wire-wall data with both the waveboy and the meteorological data as inputs. As we've seen, these only take a few seconds to run. We also haven't done much to optimize the runtime of those models. I don't think we've done anything to parallelize them, so that's only using a single compute core on a moderately spec server to go and do that. We could make it probably a bit faster if we had more time to focus on the optimization. And so we've sort of refactored all this code in by the scientists to take account to make all of this work in this station. Something like that. I think I covered that actually when I talked about the diagram. So we just did a demo of the YouTube video, but we could do a quick live demo just to show you it working. So at the moment it is loading data, and I have the choice of which site. We also found that both for teaching purposes, because this was used to teach some master students, and for our own sort of validation purposes, that it was nice to have some data sets in there that had some real examples of overtopping, because most days, neither of these locations see wave overtopping, and today is one of those days. So the reason there is nothing appearing in that graph is because today is relatively calm in Dawlish, and there isn't any waves breaking over the seawall. But if we go to Storm Bert, that happened a couple of years ago, we will see, hopefully, some evidence that there was some overtopping during Storm Bert. So it's slightly annoying how long it takes to load. We do need to do some more optimization, but we didn't have a huge amount of RSC time on this project.
He was open.
Oh, yeah. Was it in another window? Yes, it was in another window. Okay, so here's one we prepared earlier. So this is an example from Stormberg where we actually had some overtopping events. So there's no overtopping there in November up until 6 a.m. And then we start with the overtopping events and we get a metric of how frequently is occurring. We do not get from this model a magnitude of the overtopping apart from the frequency. So that could mean a wave that is slightly coming over your seawall or quite dramatically. But actually, from most policymakers' point of view, once a wave is breaking over the seawall, that's something that concerns them, and they're actually not concerned with how big the wave coming over is. If it's coming over, that's a problem. And then we also have the same data there against the sea level height, which perhaps makes it a bit more obvious as to why you're getting overtopping at that time. And again, also against the tidal graph. Actually, we seem to have had a couple of low tide here as well. Generally, you see them only at a higher point in the tide. And also, they are correlated to wind speed. So when we have the higher wind speeds, unsurprisingly, we also have more overtopping events. And if I now wanted to make this more extreme, I could. No, I can't with this one. I have to get live. No, yes, I can. They're just hidden. So if I make it more extreme, so let's up the significant wave height by 100%. Have to hit yes, yes. Then we should see a lot more overtopping coming through. Like that, and then we've got questions. Yeah. So now we see in grey is the new scenario with our adjusted forecast, and in blue is the original forecast. So we see a significant increase in the number of overtopping events. So if we look at the other graphs, now we see the significant wave height is also increased, and with it, there is more overtopping. Yes, so next steps is we'd like to provide some more, do some more data collection, and actually be able to scale this up to other locations around the world, or at least around the UK. And currently, the two random forest models are location specific in their training. We would like to build some more generalizable models that will at least partially work for any location, perhaps with a small amount of additional training being put onto them. That's it. Thank you.
Okay, so the first question is about the geophysical concept of new features which feedback contours, day-to-day, have influence on frequency of the events.
Yes, they do have a frequency on it, impact on it, but that is sort of borne out in the data we are collecting. So we don't have to explicitly put that in our model because it is shown through the data we've collected.
The optimization model loading is pre-computing the output through reloading that.
Yes, again, but we could pre-compute for the current scenario, the current forecast, but where it would be harder is to pre-compute for all the possible slider positions that you might do. So it would still take time as soon as you start tweaking the sliders if you want to experiment around what's going to happen if the wind gets slightly stronger.
Okay. Have you considered primary and secondary source size in addition to wave height to understand the potential power of a wave during an overtopping prediction, to understand the potential destructive power of a given overtopping event?
I'm not sure you'd have to talk to the scientists involved in the project. Not a wave expert.
Is there an automated way to alert policymakers to overtopping?
Not currently. This is not a live system by any means. We're not using this to, currently tell them they should shut down the railway. Maybe one day, but this is not that system yet.
Okay, for the uninitiated, tell us a bit more about the National Oceanographic Research Centre.
So we are the UK's biggest oceanographic research centre, doing research in all areas of oceanography, including both sort of coastal and deep ocean. We have 2 research ships and a number of unmanned research vehicles that we call the yellow toys. And we also have quite a few software engineers who work on many different aspects of that research, whether it's dealing with simulations like Splash or dealing with model data, sort of climate modeling, or things like marine biology data and collections of images taken of sea creatures and trying to work out what they are.
And on the other side of the fence, who are the end users of this?
So at the end of the day, the end users would be people like Network Rail, who we eventually see using something like this as a decision-making tool. This is nearly a demo from a relatively small bit of funding showing we could do this, and it does need a lot more follow-on work before we have that sort of ready for that purpose.